Hello, 8.3! We're going to be solving linear systems.
How?
Ooh! By substitution!
Toy.
Alright, so we've already learned how to solve linear systems graphically, but that's not always the best option. Sometimes it's due to the way that the equations are formatted. It's not an easy way to just graph off the top of your head. Sometimes you get answers that are decimals or fractions, and those aren't always easy to graph and determine either. So solving by substitution is one of our other methods that is going to be pretty awesome. There's a variety of steps, though. I'm just going to let you know there's 6 steps that are for sure you got to do. Step 7's optional. The nice thing about step 7 is that you could really double check that all of your answers are correct by doing that check, right? If it works in your solution works in all of the equations, then step 7 is really going to come in key just to make sure that you're confident in your response. So let's check out these steps. I'm going to highlight all of them because that's how I do. So step 1, we're going to label the equations. We're going to label them 1 and 2 so that we could reference them later.
Oh, you're going to lose all your highlighter ink.
Oh, well, I'll use another highlighter halfway through. Step 2, we are going to select one of the equations and then pick one of the variables to isolate. It really doesn't matter which equation we choose, or it doesn't matter which variable we isolate. We tend to just do whatever's easiest, right? Step 3 is we're going to then isolate that chosen variable in that equation. Sometimes it's actually already done for you. Sometimes not so much. Step 4, we're going to take that isolated variable and we're going to substitute the resulting expression for that variable into the other equation. Then we're going to solve that equation. It's going to be wicked. Step 6, we're going to substitute the value found in... We're going to substitute that value found into either of the 2 equations to find the value of the other variable. And then, like I said, number 7 is optional. But we could use that other equation to verify the solution, just to make sure that we are 100% correct. So, we are going to do that together, step by step, making sure that we feel comfortable with all of it. Step 1, let's label these guys. Equation 1. Boom. Equation 2. Step 1 complete!
Nice!
Yeah. Step 2, we have to pick one of the equations and one of the variables in that equation to isolate. Personally, I'm going to isolate for y in equation 1. So I'm going to just tell us what we're going to do here. Give you essentially little headers. We're going to isolate y in equation number 1 there. Oop, I'm going to underline it too. Bloop. Bloop. Alright. So let's go ahead and do that. So equation 1 is 2x minus y minus 5 is equal to 0. If we add y to both sides, then we can have 2x minus 5 is equal to y. I have successfully isolated it. Right? All I have to do to isolate a variable is to pull it onto one side and have everything else on the other. Alright, step 2 complete and step 3 complete. We just cranked out a whack ton of steps. Step number 4. We are going to substitute the resulting expression, so that y is equal to 2x minus 5, into the variable for the other equation. So we are going to substitute info into equation 2, right? Because we used equation 1 to isolate y. Boom. So equation 2 is 4 is equal to x plus y. But now every time we see a y, instead of y, we're going to plug in 2x minus 5. Notice that when I plug in that expression, I put it in brackets. The reason being is that it's very easy to get messed up if there's any sort of multiplication that happens before it. Of course, there's only a multiplication by 1 here, so there's really no multiplication at all. Or in case I end up having like a negative here, that negative would apply to every single term. But when I plug any value or expression in, I'm always going to do so in brackets just to make sure that I don't done goof down the road. Alright, now, since we've done that, that was step 4. Step 5 is just solve the equation. So we're solving for the value of x. So, to do so, I'm just going to rewrite this without brackets now. because I don't actually have to do anything in this particular case. I'm going to collect my like terms, and while I'm doing that, I'm going to move that 5 over to the other side. So I end up with 9 is equal to 3x. And I'm going to divide both sides by 3 to get the x alone, and I get x is equal to 3. So I have completed steps 1 through 5 already. Step number 6 is I'm going to substitute that value found, so I found the value x is equal to 3, into either of the two equations to solve for my other variable. So I'm trying to solve for y by plugging in my value of x. And we could do this for either. I'm going to solve for y, obviously, but I'm going to do so in equation 2. Because why not? I could do equation 1, it actually doesn't make a difference. But in this case, I've chosen equation 2. So if I have 4 is equal to x plus y, well, I know x is equal to 3. And to solve for y, I want to get y alone. I'm going to subtract 3 from both sides. Boom, I get y is equal to 1. Okay. So I have found my values of x and my values of y that will become my solution to my system, but I can't write it like that. I need to indicate what my final answer is. My final answer, my solution, is a point, xy, and that point in this case is when x is 3 and y is 1. Ka-chow.
Neat.
Want to try?
A little.
It's a lot of fun.
So just follow these steps, right?
Yeah.
So you're saying the first thing I would do is label these as equation 1 and equation 2?
Yep.
Okay.
Oh, dang, good.
I'm going to select one of these equations. I will pick a variable to isolate.
Which one are you going to pick?
To be honest, all 4 look pretty decent as far as options go. Man, what do I want to do? I think I'm still going to go with isolating y in equation 1.
That's fair. So all you have to do is what? Move that 4 over?
Yeah.
Seems pretty easy.
But I could do x in equation 2 or y in equation 2. Those seem like pretty straightforward options too.
That's true.
I've just chosen this one because it speaks to me. Where am I at here? Y plus 4 equals 2x. And I want y isolated. Subtract 4 from both sides. Shaboom.
Dang, you're done.
I've done the whole question.
Whoa, you're not that done.
Oh.
But you're done steps 1, 2, and 3.
Sick! Step 4, I'm going to substitute this thing in for y in the other equation. So other equation would be equation 2. That almost says 2. There we go.
Sub-info 2.
Yeah. Okay, so an F has a curve like this. A T does not have this little candy cane at the top. That's the difference between an F and a T. Today, Thibodeau learned letters. In fact, the letter that spells the beginning of her last name.
F.
Anyways, equation 2 says x minus y plus n is 0. Oh no, colors.
Yeah,
Help.
I was thinking that.
Oh.
And today, Mr. Athai learned colors.
Can you say I've learned anything if I can't demonstrate it? X minus y plus y.
Oh look, today Mr. Athai learned colors.
This color is purple. Alright, this is my equation. I found that y is 2x minus 4. That's what's going to go right in there for y. And using the world famous Thibodeau technique, I'm using brackets. Extremely important because this negative applies to the entirety of y, which means that if all of this is y, it applies to all of this. Opening the brackets and solving this equation. That's what I get. That's what I'm solving. Let me just quickly collect like terms. Negative x plus 5 is 0. Adding x to both sides. Shabam! I have my value of x. And I will now solve for y in either equation. Well, it looks easier to me. Honestly, they're not bad, either one. I'm just going to go with equation 1. Because I've already got y isolated there. It just makes things easier. So I'll solve for y in 1. And my modified version of that said that y is equal... Oh, colors. How do they work? Said that y was equal to 2x minus 4. So I'll just plug into that. X is 5. That's what we've discovered. I have found x. I have found y. I have found my solution, which I will write in a different color. X is 5. Y is 6. Bam, bam, bam. Perfectly close.
Alrighty. We can keep on just crushing this because that's how we do. And we are going to try this next example as well. Nice. So we're going to start things off by labeling equation 1 and labeling equation 2. Boom, bam, complete. We are then going to pick a variable in one of these two equations to choose to isolate. Personally, x is the only variable in equation 1 that has a coefficient of 1. Notice as y has a coefficient of 2. In the other two equations, x and y both have coefficients. Personally, I like to choose my variable by the smallest coefficient. That's what I like. But you could realistically choose any of them. So I'm going to choose to isolate x in equation 1. Ka-chow. And to do that, I'm going to write out x plus 2y plus 10 is equal to 0. I'm going to subtract 2y and subtract 10 from both sides. And I end up with x is equal to negative 2y minus 10. Oh, so nice. Next, I'm going to take that value, that expression, or that information for x, and I'm going to substitute it into the other equation. Since I've isolated x in equation 1, that means I have to substitute my information into equation numero dos. So, 3x plus 2y is equal to 6. Every time I see an x, I am plugging in negative 2y minus 10. And I'm doing that with the brackets. Right? That 3 is multiplying against x, and this whole expression represents x, which means I'm essentially distributing that 3 to every single value, or every single term inside my brackets there, so I end up with negative 6y minus 30 plus 2y is equal to 6. I'm going to collect some like terms, and while I do that, I'm actually going to move that 30 over to the other side as well. So I end up with negative 4y is equal to 36. To get y alone, I am going to divide both sides by negative 4, and I get y is equal to negative 9. Whew, so nice. Now, we have solved for one of our two variables. Now I could take that value for y and plug it into either of my two equations. Really doesn't matter what we do. I don't know. I'm feeling equation 1. It speaks to me. I'm going to do it. So, I'm going to solve for x in equation 1. I could choose equation 2, but that's just not what I've chosen today. Maybe next time you watch this video, I will. Ooh, never know. So, I have x. Ooh, that's a different color. Well, it's the same color, not the different color.
Today, Miss D learned colors.
Oh, you're right. But could you really say I've learned them if I can't demonstrate it?
You just switched.
Alright, so I am solving for x. I am plugging in negative 9 every time I see a y. So I get x is equal, x minus 18 plus 10 is equal to 0. X minus 8 is equal to 0. And if I move that 8 over to the other side, I get x is equal to 8. My final solution is a point. It is a point x comma y. And in this case, x is 8, y is negative 9. And, ooh, baby. Oh, that one was ugly. So much better. And that is my solution.
Is ka-chow what Lightning McQueen says in Cars?
Oh, yeah. I'm pretty sure, actually. Ka-chow!
Right? Ka-chow! I saw that movie for the first time, like, within the last week.
Great, now you found my source of all my catchphrases.
Your one catchphrase of ka-chow?
Maybe watch the movie again. Maybe check out Cars 2. Francesco
You've seen
Bernoulli.
Cars? I've also seen Cars. I've seen Cars too. Anyways, we're going to see a couple examples where weird things happen. The ones we did, examples A through C, they all had a very exact value. We had a value for x, we had a value for y. Super duper pooper scooper. In those cases, we have one solution, but it's possible to have infinitely many solutions or no solutions. We're going to have one example of each of those. Let's see what happens. Let's go ahead and solve this as we normally would. I'm going to pick a variable to isolate. Ooh, switch colors. Let's do that. Picking something to isolate. I'm just going to go with isolating y in equation 2. And I'm picking that because it's already done. Y is 2/3 x plus 2. So moving on to the step where I sub that in. I'll sub that into equation 1. Equation 1 says this stuff. And I'll replace that y with 2/3 x plus 2. Let's open up those brackets. Let's distribute 4x minus, all right, 6 times 2/3. What's 2/3 of 6? These days it's 4. And then negative 6 times 2. We're going to get negative 12 plus 12 equals 0. And when we collect like terms there, 4x minus 4x is 0. Negative 12 plus 12 is 0. We're getting 0 equals 0. Our variable's all gone. Where'd it go? Well, hopefully in a better place now. But if we look at this statement says 0 equals 0. Let's rewind. When is this line equal to this line? That happens when y is equal to negative 9. When does this line equal this line? Well, that happens when x is 5. When is this line equal to this line? That happens when x is 3. Fast forward, when is this line equal to this line? That happens when 0 is equal to 0. The thing is, 0 is always equal to 0. So this statement is always true. So when are those two lines same? All of the time. Wow. Well, if they're always touching, they must be the same line. Therefore, there are, well, there's more than one solution. I would say there's infinitely many. Crazy.
Whoa! I was actually gonna say whoa, but then you wrote it, so now I just read it. Any hoozles. We could see other weird things that also happen in this next example. So, what we're going to do is we're still going to follow the exact same steps as one normally would. I'm going to resort back to my favorite purple here. And our first step is we're going to choose a variable to isolate in one of the equations. I'm going to isolate for y. Isolate y in equation 1 that I've labeled already. Because it's already done for me. Right, so y is 2/3, oops, that's kind of an ugly 2. 2/3 x plus 2, boom, bam, done. Next, we are going to substitute this information into the other equation. So we're going to substitute info into 2, and here we go. So every time I see a y, I'm going to plug in 2/3 x plus 2. So I have 4x minus 6 times 2/3 x plus 2 plus 9 is equal to 0. This negative 6 applies to all of my y. So I am essentially distributing it to both those terms. So I get 4x minus 6 times 2/3 will give me 4x, and negative 6 times 2 will give me negative 12. And here I have 4x minus 4x, well that's just 0. And those two cancel each other out. And I have negative 12 plus 9, which gives me negative 3. And here I have negative 3 is equal to 0. Hold up. What Mr. Athide was saying before is, when do these two lines meet? Well, they meet when this is true. Similarly, when do these two lines meet? Well, they meet when y is equal to negative 9. In this equation here, it says, well, when do these two lines meet? They meet when negative 3 is equal to 0. But we're not silly billies. We know that negative 3 is never equal to 0. The statement is never true. Ever. Never ever. Which means the lines never touch. Whoa. Which means if the lines never touch, the lines must be parallel. Whoa!
Whoa!
Therefore, how many solutions are there? Zip, zilch, nada. There are 0 solutions. Except I write my woe differently. I go W-O-A-H. Whoa-ah!
I think song-wise, that's how it goes. But in terms of what you say to a horse, I think it's wahoa.
Interesting.
Yeah.
Next time I speak to a
official spelling.
Next time I speak to a horse.
You can ask.
Yeah. All right. So there are 0 solutions. The lines are parallel. They never touch. The statement's never true.
I asked a horse if it's actually spelled the way you spell it. The horse said nay. Anyways, settle down, everyone, and then buckle up, because we're getting into some word problems. We're gonna have to make equations for these. You can't see my hand gestures right now. My hand gestures are saying, like, what do we do? And yeah, we have to make equations. If we don't have equations, how are we supposed to solve this? Guess and check? No, because we're gonna specifically ask you to solve things algebraically. Guess and check will not be valid for when we test and stuff on this. So let's make equations. Gray? Nice and bland? No, that's not me. What am I doing with my life? Blue. Faves. Wrong blue. I'm so sorry. I got this. All right, we need a let statement. I don't even know what we're supposed to be finding. The unit price. Unit price. Highlighted perfectly. So if we want the unit price, we need the price of each apple. We need the price of each banana. Let. I will use A for apples. And remember, we're not just saying let A represent apples. That's nonsense. That doesn't mean anything. It represents the price of an apple. And we can let B represent the price of a banana. Alright. Apples cost 3 times as much as bananas. So the cost of an apple is 3 times the cost of a banana. The cost of an apple, A, is 3 times the cost of a banana. 3 times the cost of a banana. That's my equation 1. You can get a dozen bananas, 10 apples for $10.50. So if you get a dozen bananas and you throw in 10 Granny Smiths, that's going to cost you $10.50. There's my equation 2. And I can solve this. I will solve this using a technique called substitution.
Ooh.
Yeah, it's new. It's like brand new to the market. In fact, I don't even think it's even out yet. I just know some people. They supply me with it.
Ooh.
It's pretty dope. Pretty dope. Pretty dope.
You should make a video and teach it to a whole bunch of kids.
Okay. Maybe I'll do that however minutes long this video is ago.
Okay.
Anyways, I'm going to isolate this. I'm going to isolate... I think isolating A in equation 1 makes the most sense. Because it's already isolated. Doo-doo-doo. A equals 3B. Alright, that's isolated. Moving on with my life. I'm going to sub that into 2. I'm going to underline this thing. Where 2 said 12B plus 10A is 10.5. So 12B plus 10 of... Oh, that's not A anymore. That's 3B. I substituted. And we're solving that thing. 12B, 30B, that gives us 10.5. 42B's is 10.5. And B is 10.5 divided by 42, which these days is about that many. Neat. That tells us the price of a banana, but we don't know the cost of an apple. Sub this into either one. Personally, I'm going to go with equation 1. I'm going to solve for A in 1. Where A is equal to 3B. So A must be 3 times 0.25. A is 0.75. And I'm not going to state this as coordinates because this is a contextual situation. I'm going to say what their costs are. The cost, boom, diada.
Alrighty, last example. Woo! Kira's 2 years older than Desiree. 3 years ago, Kira was twice as old as... Hold up. We've seen this before.
What?
So we can go ahead and, again, define our variables, which should be similar to what we defined them to be in 8.1. And I believe back then we let K represent Kira's age. And we let D represent Desiree's age. Okay. We know that Kira's 2 years older than Desiree, so back then, and again right now, we know that Kira's age is Desiree's age plus 2. That's going to be my first equation. And we know that 3 years ago, Kira was twice as old as Desiree. So Kira's age 3 years ago was K minus 3. And she was twice as old, so she was 2 times Desiree's age 3 years ago. So 2 times D minus 3. Alright. From here, we are going to solve in the way that we always do now, by substitution. Well, we don't always do it, but in this lesson, we always do it. We do it by substitution. So for starters, we have to isolate one of the variables. Really doesn't matter which one I do in which equation, but if I look at equation 1, K is already isolated for me. So I'm going to isolate K in 1. Whoa, all this hard work. Oh no, K is equal to D plus 2. Done. Step 2. We are going to substitute that info into equation number 2. We can't substitute it into equation number 1 because that's where we isolated from. And it just wouldn't make sense. We would get some, nowhere. We'd get nowhere. We'd essentially have what we started with. So, I'm going to have my equation 2. So, K minus 3 is equal to 2 times D minus 3. Every time I see a K, I'm going to put D plus 2 is equal to 2 D minus 3. Oh, nope, silly Miss T. You forgot the minus 3 over there.
Wow.
D plus 2 minus 3. That's okay. We're all learning together.
Fair.
All right. From here, I'm just going to simplify some things. On my left-hand side, I'm just going to get rid of that bracket and combine my 2 and my negative 3. So I get D minus 1. And on the right-hand side, I'm going to distribute that 2. So I get 2D minus 6. I want to isolate my variable. To do so, I'm going to collect my terms. So I'm going to move my negative D there. I'm going to move my positive 6 over hisa. And I get 5 is equal to D. So now I know Desiree's age. But I still need to find Kira's age. The easiest way to do that is just by plugging in D is equal to 5 into my equation 1 here. So I'm going to solve for K in 1. And I have K is equal to D plus 2. K is equal to 5 plus 2. And I know what that is. It's 7. And again, because this is a contextual problem, we need to have a contextual answer. We can't just state it as coordinate points. So, Kira, how old is she? Well, she's 7. And Desiree is 5 years old. Aw, what a nice age.
Yeah. They're actually...
Oh, Kira, not Kier.
They're actually going to be 8 and 6 come July. Kira's going to turn 8 in July. Desiree's going to turn 6 in... No, wait, sorry. Kira's going to turn 8 in June. I know my months. And Des is going to turn 6 in July.
Aww.
Yeah, it's very adorable.
Happy
adorable
early
kids.
birthdays.
Yeah.
All right. That is it for our lesson, but there's some textbook homework that you